Alright. So I'll try to just use this half of the board. Okay, great. So today, we're going to do a lot of things because this is, I think, the last tutorial before your assignment is due. So my plan is to do a lot of things, like I just said, NFAs, closure properties, regular expressions, and the pumping lemma. So to be honest, I don't think I'm going to have time to do all of them in 90 minutes. So I'll probably go over, and then at some point they'll kick me out, and that'll be that. But if you need to leave like at 4, I can just, like I think this is recording. Yeah, so you should be able to just look at the recording after, okay? Okay, so like I just said, today we'll be doing NFAs and then closure properties. And then regular expressions, and then the pumping lemma. So when I say it, it does really sound like a lot. But we'll see what we can do. Okay, so I just want to start by sort of recalling why we're here. Why are you guys thinking theoretical computer science class? So remember what I said in tutorial 1, if you were there, is the whole point about this class is understanding what kinds of decision problems or like problems in general are possible or decidable and what problems are impossible to do, right? And so the way to map decision problems to a more formal object in mathematics is by mapping it to languages, right? So we have languages, something like L is AN, where N is in this set of natural numbers, and N is even. Right, so this is a language, right? And the sort of mapping to the decision problem, so you can map this to a decision problem where you ask, given N, is it even? Right, so this is what we actually care about. We actually care about knowing whether a problem is easy or not to solve. But we just have this sort of more abstract mathematical concept of a language. So how do we relate the two? Well, answering yes or no to this just really means answering is AN in L, right? So it's about mapping a decision problem to a language membership problem. So this is language membership. Okay? Okay, so that's what we've been doing. And the way that we've been studying this so far is we've been looking at DFAs as the model of computation, right? So let's see, is this going to be embarrassing? Probably. Okay, isn't that bad, hopefully. So the way that we've been trying to do this, to model this in at least the first tutorial, but you've been doing a lot more of this in class, is we've been looking at what we call language acceptors. Right, so language acceptors are the models of computers that we're designing to sort of approximate the modern day computer, right? So if we have a very simple model of computation, one that, for instance, doesn't have any memory, is not using any memory, and that model of computation can distinguish between elements in a language and not in a language, then that means that that language is very easy to recognize, or in other words, that decision problem is very easy to solve. Okay? So that's why we've been talking about language acceptors, and the first language acceptor we've seen are DFAs, right? So DFAs are, like I said, very simple models of computation because they're deterministic, and they also have a finite number of states, which really, if you've taken like a Comp 250 or something like where you look at big O notation, this just means that you can more or less use O1 amount of memory. Okay, so until you start talking about complexity theory, you're never going to really talk about the time complexity. You're just going to really talk about space complexity. And so DFAs use only O1 amount of memory, so they use a constant or like a finite amount of memory to accept the languages. Okay? And that's great, right? So that means that we already have a way of sort of categorizing some decision problems. We can say that, the L-even language or its sort of related decision problem, that's very easy. You can use a DFA, or in other words, you can use O1 amount of memory to solve it, so that's great. Another type of problem would be, something that we looked at also in the tutorial is checking for consecutive ones, right? This is also very easy because we also designed the DFA that can do that. Okay? So far so good? Any questions about the review? No? Okay, great. Okay, so again, let's see if this is... Okay, all right. I feel like I should have practiced doing that before, but what do you mean? Okay, so those are DFAs, right? Those are the sort of simple models of computation. Now we have slightly more sophisticated models of computation we're going to look at, which are NFAs. So NFAs essentially are slightly different because they use non-determinism. Right? Okay, so what does that mean? Essentially, it means that their architecture allows for multiple possible choices. So in a DFA, right, all of the states in the DFA look something like this, like if the alphabet is 0, 1, then each state will have exactly 2 outgoing edges, one for the 0 letter and one for the 1 letter, right? So it's deterministic in the sense that, if you're reading, you read some part of the string, and now you're reading a 0, and you're at this state, let's call it Q, right? Then you know exactly what you're supposed to do, right? You should go here. You should go to P, right? In NFAs, this is slightly different, because now you have multiple possible choices. Right? So for instance, from Q reading a 0, you could go to maybe P, or you can go to S. Right? So that's non-determinism in a nutshell. Okay? So for instance, oh god. I feel like that can probably be. So for instance, let's look at this NFA. I have 3 states in this NFA. I have Q0, which has a self-loop on 0 and 1. Then I have a transition with the letter 0 to Q1. And then I have a transition to the final state Q2. Right? So let's just look at what would happen if we gave this NFA an input string. Okay? So let's give it the input string, let's say 101. 101. So how is it going to use this sort of non-deterministic extra feature to run through its computation of 101? Okay, how does it actually do this? Well, essentially what it's going to do, like the main thing that an NFA actually does is it guesses where to go, and then it checks its guess. Okay? And it does this for every possible guess, right? And if at least one of the guesses leads to a final state, an accept state, then it accepts. Otherwise, if none of its guesses lead to an accept state, it rejects. Okay. So what does this look like for 101? You could start from Q0, right? Then you could say, okay, I'm going to start reading this 1. And from Q0, I'm going to decide to stay at Q0. Because Q0 is very cozy. So I stay at Q0, and now I move my pointer, so now I'm reading 0. So now what do? I say, well, Q0 still looks good to me, so I'm going to stay at Q0. Okay. And then it says, okay, well, you know, Q0 still looks good to me. Even though I'm reading a 1 now, I'm going to stay at Q0. Right? So this is one possibility of the NFA running through 101. Right? But this, right, this, of course, doesn't lead to an accept because Q0 is not an accept state. So this leads to a reject. But it's only a reject in this sort of tree branch of all the possible ways of running through 101, right? So there's another way of doing it. There's a few others. One successful way of sort of going through 101 and accepting would be, you know, you're at Q0, you read a 1, and this time you say, okay, I'm going to guess that I have to go to, I'm going to guess that I have to stay at Q0. Okay, and now from Q0, I'm going to guess that I have to go to Q1. And now from Q1, I'm going to guess, well, I have no choice, right? I have to go to Q2. Right? So in this case, Q0 was not an accept state, but Q2 is. Right? So that means that 101 gets accepted here. So this is an accept. And so the conclusion, you know, I'm not going to go through all of them, but the conclusion is because there exists at least one successful computation of 101 that leads to an accept state, that means that this NFA accepts. Right? So I will write, therefore, 101 is accepted. Okay? This is clear? Okay, great. Now, can anyone tell me what this NFA ends up accepting in terms of a language, right? Because it's a similar idea to DFAs. So there's the language accepted by DFAs, right? The language accepted by a DFA is the set of all strings that lead the DFA to one of its accept states, right? So if this is N1, then L of N1, right? The set of strings, this is the set of strings accepted by N1. So this is W in the alphabet, let's say 0, 1. So this is all the strings in 0, 1 star for which there exists a successful computation for N1 when reading W. Okay? So does anyone have an idea what that could be? Because, you know, you could start listing all of the strings, but that would take you a very long time because the list is infinite. So what do we think is happening? What is n of n1, n of n1, n sub 1 accepting in terms of a language? Let me give you 30 seconds to think. Okay, I've counted to 30 in my head. That was kind of fast. Any ideas? Yep. What's your name, sorry? Dav? Any string that finishes with 0. Any string that, very good, yes. Okay, great. So W1 is 0 star, such that W ends with Q1. Very good, right? Why? Because you can imagine, right, the NFA N1 is given a string, and now it says, okay, I'm going to stay at Q0, and I'm going to think, right? It's reading through all the letters in the string. I'm thinking, I'm going through all the letters, right? I'm going through all the letters. But at some point, I need to get to Q1, to Q2. And when I get to Q2, I can't have more inputs, right? Because if you have more letters to read and you're at Q2, then that's like that you don't finish the whole input string, and so you don't accept, right? So what needs to happen is at some point, you have to have a 0, 1, right, in the string so that you can transition from Q0 to Q1 and from Q1 to Q2. And then you can't have anything more here, because if you have more stuff here and you're at Q2, Q2 doesn't know what to do, right? So that's not a successful computation. Just because you end up in Q2 doesn't mean you accept. You have to end up in Q2 and finish the whole string. Okay? Is that clear? Okay, great, excellent. So that's what a NFA is in a nutshell. Now let's do this again. I feel like I'm not really buying any time by doing that. Okay. So another cool thing you can do with NFAs is you can have NFAs which have epsilon transitions. Okay. So what are epsilon transitions? So epsilon transitions allow the NFA to transition to a state I would say for free, or really more technically, i.e. without reading from the input tape. Okay, so what is an example of what that would look like? Let's see. So this is a bit of a convoluted example, but I have my initial state Q0, right? And I have an epsilon transition to a sub part of my NFA, which I'll say is QA, QB, QC, where the transitions here are 1, 1, oh, I need an extra. 0. Right? So I have one branch of my NFA, and then I have another branch of my NFA, which will be this guy here. Okay. So I have one branch of my NFA, this guy, and then I have another branch of my NFA, this guy here. Yes, this looks right. Okay. So basically, I have what looks like just a single string being accepted, right? And I also have an example that's pretty similar to the DFA we saw at the beginning of tutorial 1, which is like a sort of binary acceptor. Okay? So what's going on here? Well, essentially, let's say I have the string 1, 0 as the input string, right? So like NFAs and DFAs, my NFA with epsilon transition, it starts at the start state, right? It's no different. It is the start state, okay? But now what's different is it can jump to QA or to Q1 for free without reading 1, 0, without reading the first letter of the string, essentially. So why would that be useful? Well, let's see. So I have W is 1, 0. So from Q0, my NFA can again guess and say, okay, I'm going to guess to go to QA, right? So it guesses, so from Q0, it guesses without reading a string, so the pointer still stays at 1. It guesses to go to QA, right? And then it says, okay, well, at QA, I have no choice but to start reading the actual string. So now I read a 1, right? So I read a 1, I'm able to go to Q2. But at Q2, I'm now reading a 0, and so what happens here is I jam, right? So this is a jam. This is a jam because there does not exist a 1 transition. Okay. So that's no good, right? My NFA can't accept. So instead, what it can say is, let me try going, and just to make this example more interesting, let's make this the accept state. Okay, so it says, okay, this is not successful, so instead, I'm going to guess that I have to jump to Q1. So it goes from Q0, it takes a jump, right? And again, remember, when you're using the epsilon transition, you're not reading at all the input string, right? So your pointer stays at 1, and you jump to Q1, right? Now I'm at Q1, and now this just becomes a DFA, basically, because it's deterministic. So at Q1, I loop on 1. So I loop on 1, and I stay at Q1. And then I read a 0, and I go to Q2. Okay? And so this was not an accept state, and it also jammed, so you don't accept because of this computational branch. But here I finished the entire input string, and I'm at an accept state. So that means that I accept on this computation. And so the entire string is accepted, right? So you can see why I like improvise and I changed this to the accept state here, because otherwise it would have rejected in both cases, and that's less interesting. Okay, so this is very useful, right? Because what you can say is you can essentially combine different NFAs together to make a bigger one, which then accepts more strings without sort of fiddling around with a more interesting or a more complicated architecture, right? So this is just convenient because now the language accepted by N2 okay. So the language accepted by N2. Think about it for a second. What is the language accepted by N2? So it's like an NFA and a DFA. What are all the strings that lead to accept states? Okay. So I'll give you like 10 seconds to think while I count in my head. Okay. I think I've counted to 10 in my head. So what is L(n)2? So let's think about this, right? So from Q0, right, when you're trying to determine what the language accepted by any machine is, you say, okay, I start from Q0, and what are the strings I can give to N2 such that it gets to unaccepted, right? So how can I get to here, for instance? Who wants to tell me how I can get to here? Yes? What's your name, sorry?
Ria.
Ria, yes.
The string 110.
The string 110, very good. Okay, so 110, that's in there, great. See, it's good that you took that option, right? Because this is an easy answer to give. Now, what is the language accepted by this string? By this part of it? An odd number of zeros. Yes, very good. Okay, because why? Because if you're reading a 1, that doesn't change the NFA's attitude towards the string. But as soon as you see a 1, you're like, oh, I'm going to flip my bit. And because you know that when you start here, right, you're reading no zeros. So you start with an even number of zeros here. But then you read 1 0, so now you have an odd number. Then you go back, so you have an even number. Then you go back, so you have an odd. So you only go to here when you have an odd number of zeros, right? And it doesn't matter if you have an even or odd number of ones. You always stay at the same place with the ones. Okay? So what that means is the language accepted by N2 is 110. Union, what did we just say? A set of strings over the alphabet 0, 1, such that the number of zeros in W is odd. Okay. Okay, so this is less of an interesting example because this string would have gotten accepted by this NFA anyway, right? So this is not that interesting. Like this set belongs to this set, but this would have been more interesting if you said, okay, I care about accepting 100, right? Because if you have 100 here, then it's like you sort of add an edge case, right? This is kind of like when you're writing if statements and you're like, okay, for this particular case, I do want to accept. So this machine is only accepting odd numbers of zeros, right? But now you're like, oh, well, it looks like I do need to include the case 100, right? So then you say, okay, well, I'm just going to add this, I'm going to sort of hard code this case, and now I can accept that string. And that's why that's useful. Okay? Great. Okay, any questions about this? No questions. Great. Okay. So why is this interesting, right? We're talking about language acceptors and decision problems and so on. Why is this interesting? Because it turns out if you design a machine that accepts a language using an NFA, a DFA, or an NFA plus epsilon, you don't actually gain any computational power, right? All of these machines are equivalent in terms of what languages they can accept, right? So a very powerful result is this theorem, which you've seen in class, which is that the set of languages accepted by DFAs, so in other words, the set of regular languages, is equal to the set of languages accepted by NFAs, is equal to the set of languages accepted by NFAs with epsilon transitions. Okay? So what this means, right? So what this means is, right, so what? So to show that a language L is regular, so in other words, is very easy to solve, right? It just requires a finite number of memory to solve. You can design an NFA or a DFA or one that also uses epsilon transitions, right? So you can throw in epsilon transitions, you can throw in non-determinism. That doesn't sort of break a proof for regularity. Okay. So now, if we finally get to something which is more relevant to you, namely your assignment, what is sort of the intuition behind this, right? Because one of the questions in your assignment is essentially trying to see a concrete example for why a proof like this exists. So I'll show you. Oh man, I should have erased the other thing. Okay, so let me redraw the NFA. All right, that's clean enough. Okay. Okay. So essentially, I want to just give you an example of why part of that theorem is true. So why is it that the set of languages accepted by DFAs is the same as the set of languages accepted by NFAs? So this is set equality, right? So how do you prove set equalities? Sorry, do you have a question?
Oh, yeah, just.
Oh, that was it. Okay, sorry.
Or like, so we have three items, like DFA, NFA, and epsilon NFA.
Yeah.
And they're all equivalent to a regular expression that expresses the language, right? So maybe
Yes.
if one group of language is regular, I can also design a regular expression, say
Yes.
equivalent that is also.
Absolutely.
Okay.
We'll get to that.
Yeah.
Yes. Yes. Very good. Okay. So, but before we get to regular expressions, I just want to give you the intuition for why this is true. And this will also help you solve one of the assignment questions. So, like this is a set equality, right? So this set contains a bunch of languages, L1, L3, and so on. And this thing also contains a bunch of languages. So how do we know that these two things are equal, right? So if you take this direction of the proof, we have this result that the set of languages accepted by NFAs is a subset of the set of languages accepted by NFAs. Why is this true? Because remember what a DFA is. A DFA is a machine that uses determinism only, right? So essentially what it does is it chooses not to be non-deterministic. So it's basically just not using the additional feature that an NFA gives. Well, that means that a DFA is also an NFA, but one that just doesn't choose to use this very neat feature, okay? So that's an easy direction. The harder direction is this way, right? So why is it true that if you have an NFA, it also has an equivalent DFA, in the sense that the DFA accepts exactly the same language as the NFA. So the general intuition for this is that it's very similar to the product construction I was doing in the tutorial 1. You can essentially simulate an NFA with a DFA. So you can simulate NFAs with DFAs, right? How? You just sort of simulate all the possible transitions. Transitions. A NFA can make. Okay. So that's the intuition. Now, how do we do this? Let's see, I have to be smart with board management. Okay, so let's draw an NFA, okay? Meaning, let me draw an NFA. It's not like you're going to help me draw it. And let's convert it to a DFA. Okay, so this is fairly similar to the NFA we saw at the very beginning of the tutorial. Okay, except that now you'll notice, so this is similar to example 1, if you have it in your notes, but there's an extra epsilon transition. Okay? Okay, so hopefully if you took notes down, then you can see that that's true. Now, how do I take this NFA, right? Because this is clearly an NFA. 2 reasons. There's a choice for zeros, and there's also an epsilon transition, and here you have no choices to make. How do you convert this to a DFA, right? Well, like I just said, you want to consider all the possible moves your NFA can make, but in a DFA. Okay, so we'll keep the example there, and we'll test the limits of my height by doing the conversion there. Okay, so how does this work? So what you can imagine, right, is the DFA is just going to consider all the possible transitions, right, that the NFA can make at every single step, right? So the DFA that is equivalent to this NFA is also going to have a start state, right? In this case, the start state, right, the start state is going to represent the set of all start states in NFAs. So that's kind of weird in this case, because in this case, the set of start states in the NFA is 1, but in more general cases, you can have multiple start states, right? It's just that we don't see that in this version of the notes. So this is like the first step in the DFA simulating the NFA. It says, okay, let me consider all the possible start states my DFA can start from, right? My NFA can start from, sorry. And let's encode that into the start state of the DFA, okay? So now I add the start states in my conversion table, and I say from letters 0 and 1, when at Q0, when the NFA is at Q0, what states can I possibly go to in my NFA, right? So from this set of states Q0, when I read 0, where can I go? So it looks like from Q0, I can go to myself, and I can go to Q1. Right? So I'm simulating my NFA. So I say, from Q0, when I read a 0, where can I go? I can go to Q0 and to Q1. No one's stopping me. There's a mistake here. I put it there on purpose. Yes?
Can you also go to Q2?
Aha! Maybe you can also go to Q2. How can you possibly go to Q2?
Because like the epsilon.
Yes! Very good. We can use epsilon transitions. Great. We're using something that we just learned. That's the point of teaching, I think. So from Q0 when reading 0, right? From Q0 when reading 0, what can your NFA do? It can say, okay, I'm going to read this Q0, right? So now it's reading the 0, but now it can take this jump for free to Q2, right? So be careful about these things. They're very subtle, and they can trip you up. So always be aware of the epsilon transitions. This is the takeaway. So indeed, I can also go to Q2. Aha. Right. Very good. Now, how about the set of states containing Q0? Where can I go when I read a 1? Anyone want to help me? 0. Q0. Yes, very good. Excellent. I can go to Q0, right? So what does that mean in terms of my actual machine? In terms of my DFA, right? Well, when I'm reading a 1, I just go back to myself. And when I'm reading a 0, I go to a new state. That new state is Q0, Q1, Q2. So notice what's going on here, right? The DFA, the states of the DFA are encoding information, right? When you're designing DFAs, remember that was a trick I gave you in tutorial 1. When you're designing DFAs, you want to make each state do something, or like remember something, right? So the start state of my DFA, it encodes all the possible start states of my NFA, right? Then this 0, 1, 2 state in my DFA, it represents, right? It represents all of the possible states my NFA can go to when from the start state it reads 0, right? So I'm encoding information in my DFA directly, and in this case the information is all the possible ways I can get to, all the possible transitions I can go to from Q0 reading a 0. Yes. Okay, very good. Now, let's do this again, right? Because now what's happened is I need to make a DFA, right? So I can't just do this like this. What happens when I'm at state Q0, Q1, Q2? Right, so I'm here. I'm here. Now, I'm at states Q0, Q1, and Q2, right? So you can imagine the NFA is at all 3 of these states at the same time. And now it reads 0 from all of these 3 states at the same time. Well, where can it go? Well, because from Q0 I can go everywhere. Of course, if I have a set of states that has Q0, and Q0 can go everywhere from reading a 0, and of course, it can also go from anywhere, right? It can go to anywhere. Jeez, prepositions are hard. Okay, right? So I can go to the set Q0, Q1, Q2, reading a 0. What about when I read a 1? When I read a 1, well, let's see. Let me go through each of the states, and let me see where I go when I read a 1. So from Q0, when I read a 1, in my NFA, I go back to Q0, and that's it. Then the other state here is Q1. So when I'm at Q1, and I read a 1, I can use this transition and go to Q2. Right? So I can also go to Q2. I could use this epsilon transition, right, to go to Q2, but then I would have a 1 to read, and that would be a jam, so that wouldn't really help. Okay. Then let's see, for Q2, when I'm reading a 1, I always jam, right, because there are no transitions. So that allows me to close my set of states here, and I have Q0, Q2 here. Okay, great. So now let's add this other state to the table and to my diagram. So when I'm at Q0, Q1, Q2, from 0, I go back to myself. Then when I read a 1, I go to this new state, Q0, Q2. Okay, great. And now I do the same thing. So I'm just going to skip the theatrics and just write down what it is, given that we're already pretty short on time. So you can check that this is right. So you go to these set of states from 0 and this set of state from when reading 1. Okay. So what that means is when you read a 0, you go back here. And when you read a 1, you go back here. Okay, fantastic. So what is the language accepted by this DFA? It's a trick question. Now it's not a trick question because I told you it's a trick question. It's the same, is it?
We don't have such
We don't have accept states. Very good. Meaning?
No, no.
Very good. So in this case, right, I've missed a very crucial step in my conversion algorithm. I have not added the accept states. So if my DFA has no accept states, it accepts no strings, so it accepts the empty set. Okay? So now what I need to do is I need to add the accept states to the DFA. And the accept states of the DFA are all of the states that contain at least one accept state from my NFA. Right? And that's intuitive, right? Because if the DFA, when it's simulating the NFA, it goes here, that means that the NFA, right, it has branches of computation. One of them ends up in Q0, and another one ends up in Q2. Q2 is an accept, so that means I should accept, right? So it makes this an accept state, and it makes this an accept state. Okay. And as an exercise, I'll leave this for you. What is, let's call this N1 prime. What is the language accepted by N1 prime? Okay, great. Any questions about this so far? No questions? Yes, question.
So you don't need to write like Q1 and Q2 as like individual states in whether join and out or through? Only like.
Okay, that's a good question. So the question is, do I have to add, the states Q1, Q2? If you wanted to use the so this is a greedy algorithm to convert the NFA to a DFA. If you wanted to use the sort of very slow brute force algorithm where you create all the possible set of states, then you would have to do that. But if you're using this algorithm, it's fine to just use the reachable states. So basically, no, you don't have to add Q1, Q2, or like Q2, or yeah.
And if I would draw out, let's say Q1, Q2 in like my DFA as well, as Q2 basically all like transitions lead to that state. Because like Q2 doesn't have outgoing transitions in the NFA, then any like if at Q2 I'm receiving a 0 or 1, I'm going to that state.
Yeah. So like that's a jam. Like the technical term is a jam. So if you head, like imagine I had a 0, 1. So I read a 0 and I went to Q1, and then I read a 1 and I went to Q2, and I had another like letter, maybe 1. Then here, because I have no transitions, it's a jam, and that's just like the NFA doesn't know what to do, right? So jams, and it's like you can kind of think of it as if you're going to a dead state. Sure, yeah. Okay, so great. Now, one thing to mention is there's another question in the assignment about so doing something like this, and then there's something about complements. Okay, so I just want to give you a quick perspective on this. So in DFAs, right, so this is just to cover my bases to make sure that I talk about all parts of the assignment. In DFAs, everything is deterministic. Oh, well, this is slightly different, right? Everything is deterministic. So here, if this is a DFA N, or let's call it N, yeah, then the language accepted by the DFA N is the set of all strings that go to one of the accept states, right? So in this case, there's just one. So now if I ask you, what is L of N complement, right? If I ask you what is L of N complement, so in other words, L of N here it's fairly similar to a DFA we just saw, except that in this case, it's where N1 of W is odd, right? The complement here, I'm asking for what is the set of states that are not in L of N, right? That's all of the strings that do not have an odd number of ones, right? So L of N complement. is n of n, the number of ones in W is even. Right? Just by definition of complements, right? This is, I'm just dealing with set theory at this point. I'm not talking about DFAs or NFAs or anything, right? So the neat thing, right? The neat thing is in DFAs, because everything is deterministic, right? The set of all states, the set of all states in your DFA, they're going to have, if you give any string, yeah. So if you give any string to your DFA, right, and the DFA runs through its computations, it's going to end up in one and exactly one state in your DFA. Notice that's not necessarily true in an NFA, right? An NFA, if you give it an input string, the NFA could end up in two states, right? So then, if you say for DFAs, if you know that every input string ends up at exactly one and only one state, then you can say, well, take all of the accept states, right? Make them not accept states, and take all of the not accept states and make them accept states, right? So just do something like this, right? And almost by definition, right? Almost by definition, all of the strings which go to accept states in the DFA, now they get rejected because now these are no longer accept states. And all the strings that used to go to reject states, they now go to accept states. So almost by definition, if you do this switch where you take all the accept states and make them reject, and all the reject states and make them accept, you build a machine that accepts the complement of the language accepted by the DFA. So be careful, this is not true. This is not true if you have an NFA. So this is an NFA, right? It accepts all the strings that end in 0, right? So this is an NFA. If the NFA receives an input string that ends in 0, then it goes to an accept state. Now, if I do this conversion trick, I get something like this. Okay? So this accepts, this is N1, N2, so this accepts W ends in 0. Okay, now what does this accept? Everything, very good, right? This has a start stage, right, which is an accept state, and it has a self loop for all the possible strings, all the possible letters in the alphabet. So if you give the NFA any string, then it can just say, okay, well, this is a great place to stay. I'm just going to self loop all the time with the input string and stay here, right? And so notice this is definitely not the complement, right? So be careful about that. Okay. So I've talked about the complement, which is what I wanted to do. Now let's talk about closure properties. So let me not erase this part. Okay. Great. Excellent. So now we're going to talk about closure properties, which we've kind of indirectly talked about already. So what are closure properties? An example of a closure property. So closure properties to be specific for regular languages. So closure properties are essentially set or language operations where when you apply them to, in this case, regular languages, the resulting language always remains regular. So that's a closure property. So for instance, there's a closure property about the union. So if L1 and L2 are languages in sigma. So sigma is just some non-empty alphabet. And we say that L1 and L2 are regular. Then the closure property is that, let's take the union L1 union L2 is regular. Okay? So this is an example of a closure property, which you've seen already in class a few lectures ago. So the interesting part of closure properties is really showing that they're true. Okay? So how do you show in this case that this closure property is true? Well, the claim here that's being made is that the union of these two regular languages is regular, right? So what you need to do then is you need to show that for any L1 and L2, for any arbitrary language L1 and L2 that's regular, you can build an FA, right? Maybe a DFA, maybe an NFA with epsilon transitions. You can build some kind of FA which accepts the union of the languages. So how do I do that? Well, in this case, I start with my assumptions, right? So I know that L1 is regular, and I know that L2 is regular. So what do these two things mean? By definition, right? By definition of regular languages, that means that there exists a DFA M1 such that the language accepted by M1 is L1. And similarly for M2. Right? So I have some two DFAs that are able to accept L1 and L2 respectively. I know this by assumption, right? So, I don't know exactly what the DFAs look like, so let's just use boxes to represent them. Okay. So now, right, now what I want to do, if I want to show this, right, so if I want to show, WTS want to show, so if I want to show that L1 union L2 is regular, in other words, what I need to show is that there exists some FA, let's call it M prime, such that L of M prime is equal to the union. Okay? So the trick in all of these sort of closure property proofs is you want to somehow use the machines that you started with to build a larger, probably a larger, machine M prime that accepts the sort of resulting operation of the languages. Okay? So, anyone have, well, you've probably seen this in the lecture, but, so this is a good test of if you were paying attention. Does anyone have any ideas of what I could do, right? What can I do to build an FA M prime that accepts the union of the two languages? Product construction, that would be good for the intersection. It would also be good for the union. So yes, okay, product construction would be one way of doing it. How about if I am somehow forced to use epsilon transitions? Yes?
We can use the addition of both the DFAs, so we get an epsilon transitions.
Aha. Yes, very good, excellent, very good idea. So the idea that was just mentioned is, well, I want to accept the language that's the union of both languages. So, this machine M1, it accepts strings, right? It accepts all the strings that go to, these accept states, right? And the machine M2, it's the same thing. It accepts all the strings that go to all of these accept states, right? So now I want to build a machine which, given a string, right, it checks if the string is in either one of these two languages. If yes, then it accepts it. Otherwise, it rejects it. Well, what the bigger machine can then do is it can say, okay, I get some input string. So I get some input string W, And I just guess, right? I say, well, maybe this W is going to be accepted by M1. So I take the string W and I say, okay, I'm going to give it to M1. Okay. Then M1 does its thing. It's a DFA, so it does only one thing, right? It goes through the computation, and then maybe W ends up in this state, right? So that's a reject in that case. So then the DFA is like, oh, that's too bad. Let me try my other possibility, right? So in this case, I jumped, right? I use an epsilon transition to go from my start state to M1. That didn't work, so I say, okay, well, instead of doing that, let me jump to M2. So I use another epsilon transition, and I jump to the start state of M2. M2 does its thing, right? And then, lo and behold, W gets to this accept state, right? This is an accept state of the larger machine, right? So that means that M prime has at least one branch of computation where it ends up in an accept state when it's reading W, right? So then it accepts it. Now, if W was neither in L1 or L2, right? If it was in neither, then M prime would have said, okay, I'm going to start with this one. That's not gonna get me anywhere. Maybe I get to this non-accept state. So then I try again. Then I get to this one. That's not an accept state. So in both cases, I don't get to an accept state, meaning that I reject. Okay. So then the machine, the bigger machine, would just be an extra state here. I'll just have to add an extra state here, and make this the entire machine. Okay, is that clear? No one's nodding. I need one nod. Good, one nod. One nod is enough. Okay, great. So this is easy, relatively speaking. Let's look at a harder case. Okay. I feel like there's no advantage in doing that at all. Other than maybe looking cool. Okay, so let's do another example. This other example is going to be, again, about two languages. So suppose I have two languages that are both regular, and I want to show that merge L1, L2 is regular. Okay, well, what is merge? I have to define it for you. So merge L1, L2 is the set of strings let's just say sigma is not empty, where essentially what I do is I take strings from L1 and I cut them into two pieces, and I take strings from L2 and I also cut them into two pieces, and what I do is I take the second piece from L1 and the first piece from L2, and I stick them together to get x2, y1. Okay, so hopefully this reminds you of something. I won't tell you what. Now, what's an example? What's an example of what this could sort of give you? Imagine my alphabet is AB, and L1 and L2 are some complicated languages, so let's just consider the first string. So the first string in L1 is ABB, and the first string in L2 is AAA. So there's more strings. Okay. So this tells me that I have to consider all the possible sort of ways of cutting up the string. But let's just consider one just for illustration purposes. So let's imagine for L2, for L1, X1 was AB, and X2 was B. And for L2, y2 was AAA, and y1 was the empty string. Okay. Notice I can do this. This might be surprising to some of you, but I can do this, right? Because in the definition of my language, it says that strings can be in sigma star. Sigma star includes epsilon. So it's fair game to say y1 is epsilon and y2 is the rest of the string. That's fair game. Okay. So then in merge L1, L2, what would I have? Well, I would have the second part of this string, so B, and the first part of this string, so epsilon. Okay? So this would be an example of a string in merge L1, L2. And now you can imagine you do this for every single sort of partition of this string and of all the other strings, and every single partition of this string and every other string, right? And then you get merge L1, L2. Okay, so this is a pretty complicated operation, right? It's much more complicated than the union. So we're going to have to be slightly more creative in showing that for any L1, L2 regular, merge L1, L2 is also regular. So how are we going to do this? Let's consider arbitrary DFAs, M1 and M2, that accept L1 and L2 respectively. So this is always the trick. You always want to sort of think in your head, I want to simulate strings being accepted in the machines that I sort of know I can assume exist, and then I want to see how I can sort of combine them together or do some interesting things to accept the more complicated language. Okay, so this is my sort of imagined DFA M1 for the language L1, and this is my imagined DFA M2 for my language L2. Now, let's consider these two examples again, right? ABB. So ABB is in the language, right? Now remember, what it means for a string to be in a language, which is accepted by a DFA, it means that that string gets to an accept state, right? That's a very important thing to remember, right? So the string is special in that when M1 reads it, you know, maybe it has a transition A here, and a transition B here, and then another transition B here. This necessarily has to be an accept state, right? So that's important, right? Because if you knew nothing about what this had to be, then it would be very difficult to do any kind of proof. Okay? So then, similarly, let's imagine for M2, it doesn't really matter what the actual structure is. Let's imagine for M2, we had something like this. Right? So this, when it's given ABB, the machine M1 goes here, then it goes here, then it goes here. Whereas for the machine M2, when it's given AAA, it goes here, then it goes here, and it stays here. Right? Okay. So now what I want to do is I want to create, right? I want to create a machine M prime, which is going to sort of simulate this operation of merging, right? And accept the string, the input string, if and only if that operated string is in merge L1 and L2. Okay? So that was a lot of words. Essentially, I need to create a bigger machine M prime. Okay. I need to create a bigger machine M prime, which, now this is a bit counterintuitive. What should M prime do? M prime should accept the string B, right? So it should accept the string if I get the input string B, I know it's in merge L1, L2, right? So I need to accept it. how can I do this? Even though this seems really complicated, it just boils down to trying to simulate what M1 and M2 would be doing. Okay? So, let me give you 30 seconds to think about it, and for me to have some tea. Okay. Yes.
So when you say like accepting string B, you're saying like in general accepts x y x2 y1, or you're saying we're talking about an n prime to accept x2 or?
No. So we want to design an M prime where the M prime gets an input string W, and then essentially what it needs to do, it has to check if that input string W is in merge L1, L2. So to check that it's in merge L1, L2, the machine M prime has to kind of guess that the first part, some first part of its input string is x2, right? And then check that that's indeed a possible x2. And then transition to then checking that the second part of the string is y1, and that this is a valid y1 for the machine M2.
Basically, it's like when we got the input string, and then it must like starting from any of the intermediate state, it can reach a terminal state of M1, and then you switch to M2, and then start in recognizing until it gets to another terminal state in M2, then this string is accepted in M1.
Yeah, so that's a good blueprint of what to do. You have, so I think you more or less have it. There's something that you don't really need in what you just said, and so I'll get to it. Any other ideas? No. Yeah?
Well, maybe that's what she said, but like, is it, like the idea would be that if you take, just like consider y1, we accept like y1 if it could potentially lead to an accepted state in M2.
Yeah.
So we could kind of work backwards from the final state and take all the states that can reach it and make them final states of like n prime.
Good.
And then to get there, we know that we need like an x2 in the m1. So then we do basically like the same idea for m1, which is like working backwards until we find strings.
Molto bene. Very good. Yes. So exactly what he said. Now let's just do it pictorially, rather than just with words. Okay. So what do I need to do? I get my machine M prime gets B, right? It gets an input string B. Now, what does M prime have to do? It has to check if B could ever possibly be in merge L1 and L2. So what it has to do is it has to say, well, I have to consider every possible way of reading this this input string B, right? And considering every possible way of decomposing it as, in this case, x2 and y1, right? So essentially, let's do, yeah. So let me give you the blueprint of what this looks like. So I'll first write it in words, and then I'll give the sort of more formal mathematical definition. For the assignment, we expect you to give the formal mathematical definition. The English just sort of helps the markers understand what you're doing. Okay, so the blueprint, so I'll just write blueprint for M prime. Okay. The first thing it does is it says, okay, I'm given the string B, right? I know that for B to be in merge L1, L2, the first part of the string, so B, has to be x2, right? So I'm going to guess that B is x2, right? So what the machine M prime does is it guesses where, so it's given W is the input string, guesses where x2 ends, right? So W is the input string I give to M prime, and so what the machine M prime does is it says, okay, I'm going to guess that at this point, that's where the substring x2 ends, right? And the substring y1 begins. So I guess where x2 ends, right? Now I have to check this guess, right? So guess where x2 ends and check the guess, right? So how do I check my guess? I check my guess by saying oh, right. So I check my guess by saying in M1, right? In M1, if I guess that my string x2 is B, let's say. So if I guess that my string x2 is all the way to B, right? Then I need to say, well, that means that this was the B that got me to an accept state. So I have to check that it's possible with this B, right? With this part of the substring x2, I'm able to get to an accept state in my machine M1. Okay. So I need to check the guess by determining whether there is an intermediate state in M1 such that when it reads x2, it gets to a final state of M1. Right? So this makes sense, right? It makes sense given what I'm trying to do, right? So I have this string A, B, B, and its first part is x1 and its second part is x2, right? So in the machine, right? In the machine, what that means is that at some point, right? At some point, if I stop here, this can be x1 and this can be x2. The remaining part of the string, the x2 part of the string, it's going to eventually get to an accept state of my machine M1, right? So what I need to do, what M prime needs to do is it needs to say, okay, imagine the first part of the string was AB, right? Then it gets to this state, and then suppose that that was my guess, then I have to check that I can get to this accept state, right? So M prime a priori doesn't know, right? It has nothing, it has no idea about M1, right? So it's going to say, well, imagine if I started reading B from here, right? Then if I read B from here, I get maybe somewhere here. That doesn't get me anywhere. Maybe I can read B starting from here. Well, that doesn't, or starting from here, well, that doesn't get me anywhere. That gets me to a non-accept state. But then from here, I can actually manage to reach an accept state. Okay. So that's the first thing I do. And then at some point, right? So I'm given the input string B. Right? I guess. Okay. I'm given the input string B. I guess that this is the first part of x2 of the string, and this is x2. So I guess that this is x2. And then I check my guess, right? So I'm just re-explaining because I didn't think I did a good job at the beginning. So I guess that this is the first part of my string, this is x2. Then I have to check my guess, right? Because I have no idea if this was right. So I go and I say, well, start from any of the states, in M1, and read the string. Because this string is supposed to be the second part of this string, right? Then, if I had read this entire string, I would have gotten to an except state. So I just have to check that. Okay? So then I check this part, right? I check this part, and then I say, okay, I'm done checking. Now I read this second part of the string, which I'm guessing is y1, right? So what I do is I say, okay, I'm gonna jump to M2, and I'm going to read this string, right? So I jump, so once I finish this, gets to a final state M2. Then the second step is to jump to the start state of M2 and reading the rest of the string. If M2 ends in a state which can reach one of its accept states, then accept. Okay? Does this make, I think this is more or less what you were saying. Yeah, great, excellent. Okay, so this is the sort of blueprint. Now let me show you how this is actually done formally. I'll let you finish writing this part. Okay. So writing this is unfortunately not enough for the assignment. What you need to do is you have to give sort of a formal construction of the FA you create. So how you can do that is you say, well, I know that I have two machines, M1 and M2, which are DFAs. Let's call this S1. Yeah, S1. Okay, so I start with these two DFAs, right? And now I have to create an FA and prime, which is going to have some set of states, the same alphabet, transition function, start state, let's call it prime, and then a set of exceptions. Okay, so what's the set of states for M prime is going to be? So let's draw this picture again. Okay, so I'm trying to design M prime. Okay, and I get some input string. The input string, these are each letters. Each of these are letters, right? And what I say is my M prime is first going to say, okay, I'm going to guess that this, at this point, this is x2, right? I guess that this is my x2, and then I check in my machine that this is a possible x2. So how do I do that? I say, well, I'm going to have the start state, right? And I'm going to guess that this x2 part that gets me to an accept state is maybe this state, right? So I have to be able to get to here, right? So I have to be able to get to here and then simulate reading x2. So that tells me that I need to sort of be able to jump to this state, this intermediate state, and then read x2. But maybe this is wrong, right? Maybe if this is like ABB, and I read ABB from here, I don't get to an accept state, right? So then I have to say, well, I have to guess jumping to maybe another state, and then reading ABB, and then to another state, right? And so the idea here is I can't guess what the correct state is going to be. So what my machine M prime has to do is it has to try all the possible guesses, right? So it's going to say I'm going to jump to every possible machine, and then so it's going to run through reading x2 for every possible jump, and then at some point it's going to say, okay, well I'm done reading this part. Now I'm guessing that this part is y1, so I have to jump with an epsilon transition to the start state and read y1 from here. Okay? And then I accept y1 if and only if this state allows me to reach an accept state. What time is it? Oh. 3:55? Okay. Okay. Right. So I should have just started with this explanation. I think it's a bit clearer than the mess I wrote just before. Yeah? Yeah, a little bit? Okay. So then what does that mean Q prime has to be? Right? Well, that means that Q prime is the set of states from M1, right? So I'm using the set of states from M1. Then I'm also using the set of states from M2. And then I use an extra state here, right? So I use an extra state here as my start state. Okay? Okay, good. So then the start state Q0 prime of my machine, or let's call this S prime. So then S prime is going to be defined as Q0, right? And then I have to create the transition function, right? So the transition function of my machine, right? My machine is going to accept a state. It's going to be at a state, and it's going to be reading a letter. And so this is the standard way of defining transition functions, right? You have a state, and you have a letter, and you tell the machine what to do at every single possibility, right? So what do I do? Right? So if Q is the start state, then what I need to do, so that means that I start here. Then I use the epsilon transitions to jump to every single state here, right? I'm going to jump to every single state because each of these possible states could be the part I get to once I read x1, and then I have to read the rest x2 to check that that was a possible input string to m1 that got accepted. Yeah? So what that means is I'm only going to say transitions for the epsilon transition. And what I'm going to say is this is going to be, in this case, I'm going to be able to transition to all the possible set of states here. So that's Q1. Right? So I can jump to any of the possible states. Okay? Then, imagine I jump here. Then what I want to do is I want to be able to read this part of the string. Right? I want to be able to read this part of the string. So what I need to do is, if Q is part of Q1, sorry. If Q is part of Q1, meaning I'm in this part of the machine, then I just have to simulate. I have to simulate the machine M1 reading the string. Right? So that would just be Q reading sigma. And let's assume that sigma is not the empty string for epsilon. Well, I guess there is class after this. Damn. Okay. So notice that I put this in a set, I put it in a set because if I'm designing, in this case, this is an NFA with epsilon transitions, the output type of this transition function has to be sets. Okay. Okay. So now, imagine I jumped here. Now I'm reading this part of the string. Reading this part of the string. If I happen to be lucky, right? If I happen to be lucky, and I'm at a final state, right? Then I'm going to say, okay, then that means that this part of the string, it was able to get me to an accept state, meaning that I could have had, x1, whatever, and then x2 get me to the accept state. Now what I need to do is I have to check that this part of the string can get to a state where you could stick another string that gets me to the accept state. Okay, it's very convoluted. This is a very convoluted example to explain, but it's very useful. Okay, so what does that mean? That means that I have an extra condition that if I'm at a final state of my DFA M1 and I have an epsilon transition, then I jump to this accept state. So I jump to the start state of M2, which is S2. Okay? And then, so now I'm going to be in my machine M2. So I'm going to be in my machine M2. So if Q is in Q2, right? Then I'm just going to simulate my machine M2 reading the rest of the string. So that just looks like the same thing here. Q sigma. Okay? Okay, great. So then I keep reading, right? And the only thing I need to check that I don't get to a state that's kind of like a dead state. So to define f prime, I just say it's all the possible states in Q2 such that there exists a string in sigma star where using the extended transition function from Q reading W, I can get to a final state of M2. So this is a bit of a hack. You can just think of this as like a reachability function, which you can definitely use because this property is decidable, which you haven't really seen yet. But you can use this kind of condition to define a reachability operation. Okay, unfortunately I have to stop, but I have probably one more hour of content. So not sure what I should do. I do have office hours now. I will record the last part that I was going to give and then post it. So because I think it would be very useful for the assignment. And yeah, that's it. They're going to be in 110. So the same place as all the other ones. F prime is the set of accept states of the machine M prime.
It's like you're saying the final states are